All right, so let's consider some arguments against hypothesis testing within frequentist inference. So the first one is one that we've talked a bit about in the context of the introduction to the course and interpretations of probability. And this one is what Aubrey Clayton calls Bernoulli's fallacy. This is sometimes called the base rate fallacy, at least in a specific context, and also sometimes called the prosecutor's fallacy. Bernoulli's fallacy is sort of an attempt to be a bit more general than something like the prosecutor's fallacy that is specific to courtrooms and logic there. So Clayton, in the book Bernoulli's fallacy, makes this distinction between inferential probabilities and sampling probabilities. And an inferential probability is a probability that points at and is assigned to a hypothesis or a parameter. And a sampling probability is a probability calculated under the assumption of a particular hypothesis or parameter and is assigned to data. So it's subtle, but the probabilities are assigned to different types of things: hypotheses in terms of inference and data in terms of sampling. And Clayton and others suggest that frequentist inference is really confusing these two, that a p-value is technically a sampling probability, that's true, but that frequentists sometimes use it as an inferential probability, and that's wrong. That would be a fallacy. So let's just do kind of a basic example to understand how one might make this fallacy. Simplified example. So imagine somebody, Jonah, a healthy person, notices loss of taste. This is a symptom of COVID, and he takes a COVID test, and it's positive. So we'd like to know, what are the chances that test is wrong? Jonah doesn't want to, quarantine if he doesn't have to, miss class, whatever. And to compute the probability that the test is wrong, we need some information. And we know that the test is pretty good. If somebody has COVID-19, the test correctly identifies COVID-19 in 95% of cases. And that would be, the probability of a positive test given COVID. So given that somebody actually has it, is 0.95. In addition, the test, we're assuming, wrongly claims that a person has COVID-19 about 1% of the time. So that would be the probability of a positive test given that they don't have COVID. So that would be an error, is about 1%. And notice that these are not, it's not that one of these is one minus the other. These are conditioning on different things. So we'd like to know, what's the chance that Jonah has COVID-19? What's the chance that the test is positive? What are the chances that he has COVID? So let's just write out that probability. So we'd like to know the probability that Jonah has COVID given the positive test. And so if you know anything about these kinds of problems, you know that you should use Bayes' theorem. And we have some values for Bayes' theorem right now, but we don't have others. So we have the two probabilities that I mentioned on the previous slide, the 95% and the 1%. And those are likelihood values in Bayes' theorem. But we also need a probability of evidence, which we'll get from these likelihood values. And we need prior probabilities. So in this context, prior probabilities are the base rate of COVID in some relevant population that Jonah is a part of. So what is sort of the prevalence of having COVID in the state where Jonah lives or the town or whatever? So we need that kind of probability in order to answer this question. And this is something that frequentists don't utilize, and Bayesians are saying as part of Bernoulli's fallacy, they're doing inference wrong because they don't make use of a prior. So, if we assume that the prevalence in the population is pretty small. Maybe 1% of people at a given time have COVID-19 and 99% don't. We can use these values to compute the posterior probability, and this posterior is the probability that we're looking for. This is the probability that Jonah has COVID given the positive test. So that's what we're looking for. The evidence is just that denominator of Bayes' theorem that can be written using the law of total probability. So it's the probability of a positive test, which is hard to compute on its own, but we can use the law of total probability to compute it with quantities that we have. So I'll just write this. I'll move this up a little bit. Oops. And I'll add down here. So probability of a positive test but not having COVID times the probability of not having COVID. And then, of course, these priors are the probability of having COVID and not having COVID. So you can just plug in the values to get the evidence. It turns out to be 0.02. They're the same for each one. And then Bayes' theorem is the likelihood times the prior divided by the probability of the evidence. And so if you do that computation, it turns out that you get 0.475 for the probability that Jonah has COVID given the positive test, and then 0.525 for the probability that he doesn't have COVID given positive test. So this would suggest that it's actually not super likely that he has COVID, even though the sampling probability was high, right? So the test correctly identifying, we could think about that as a sampling probability. That's quite high, but the probability that he actually has it is, less than 50-50. So the odds are a little bit in his favor. And just the idea here is that Bernoulli's fallacy is just not using Bayes' theorem to compute the answer to this question. And frequentists don't use Bayes' theorem to compute the answer to this question. They might do a hypothesis test where they set up a null hypothesis that Jonah doesn't have COVID and try to gather evidence against it, say with a probability of a positive test given that somebody has COVID. That would be a misalignment using sampling probabilities for inferential probabilities. So the frequentist response to Bernoulli's fallacy is basically that probability is not the right kind of a thing to assign to a hypothesis. And so the frequentist says this move right here of assigning probability values to this specific hypothesis that Jonah has COVID-19 is not appropriate. This is a single case. It's not the sort of thing that can be repeated. It's not the sort of thing that's probabilistic. Jonah either has COVID or doesn't. And so assigning a prior is inappropriate, and then moving through and assigning a posterior is also inappropriate. It's not something that you should assign probabilities to because the probability is either 0 or 1, these extreme cases, right? And they want to block the idea of using probability as meaning something subjective or the right way to quantify evidence. All right, so this gives us a sense of an objection to frequentist inference, Bernoulli's fallacy, and how a frequentist might respond to this objection.